Now, what about Newton's second law? What does Newton's second law say? So it says here, the rate of change of momentum of a body is directly proportional to the net external force acting on it and takes place in the direction of the force. Now, basically, there are many things that we can get from this second law. The first thing is we can actually derive the equation of F net equals to MA from here. Alright, so we need to know how to derive the famous equation F net equals to MA from this equation. Now, for example, let's start off with what they say. So the rate of change of momentum means dp dt lah. Alright, if some people are not familiar with differentiation, then you can also write as delta P over delta T. Doesn't matter lah. So rate of change of momentum lah. Now, that's what it says. Okay, so then what you can do is, you can break down the momentum to MV right now. Then you must tell them for a body of constant mass. Now, why you must tell them body of constant mass? Because in actually Newton's second law, there are two branches from this. What we learn in A levels is for constant mass. So what we can do, we can take out the M. Then it becomes dv dt right now. So once you have dv dt, then you remember that you can change proportional to equals. But from proportional to equals, you must put a constant in front. So you get k m dv dt. And remember, dv dt is rate of change of velocity, which is also called acceleration. So you get F equals to kma. How do we get rid of k? It's actually by definition of 1 Newton. You see, 1 Newton is defined as the force when acting on a mass of 1 kg will produce an acceleration of 1 meter per second squared. So the definition, if I substitute 1 here, and my mass is 1, my acceleration is 1, what must my k be? That's how you get rid of the k. That's how you get F net equals to ma. So what it tells you is, for body of constant mass, that's how you derive the equation. But there's another branch which we don't learn, which is for a body with constant velocity, but the mass changes. That means there's another branch where you get body of constant velocity, so your F net equals to velocity dm dt, which is usually used for the case like sand dropping on the conveyor belt. So as more sand drops onto the conveyor belt, the mass increases, but the conveyor belt is still moving with the same speed, which we don't learn in our syllabus. Which is why when you derive F equals to ma from Newton's second law, it is important to write this before you can change from here to here, before you can take out the mass. So don't forget that. Okay? Alright. Now, some people ask me, is that the only way of deriving this? Okay, so I'll teach you another way. Now, you can also derive this F equals to ma from the definition of force. So if they ask you to define force in terms of momentum, you can also define force as the rate of change of momentum. So this is acceptable as well. So from this definition, we can also derive straight away. So if they ask you to define force first, which is F is the rate of change of momentum, you straight put delta P over delta T, which means to say you don't have the directly proportional symbol. If there's no directly proportional symbol, then you won't have a problem with K appearing later on. Understand? So why they can define force this way? Because they know K is 1 anyway. So they can also define force this way. But Newton's second law, you must say directly proportional. But when you ask you to state the definition of force in terms of momentum, then you say it's straight away, force is the rate of change of momentum. Don't they put directly proportional. And if they ask you to derive second law, they derive F equals to ma from this, then you can straight away put there mv over delta t, and then you must tell them for constant mass, then only you can take out the mass, and it becomes delta v over delta t, and then you get your ma. So you notice there's no problem with the k coming. Also can. Okay, so the two ways to derive the equation. So what are the implications of second law to us? What is the importance? Now, since your formula F net equals to ma comes from this Newton's second law, right? So what is the implication? Number one, it is your net force that causes acceleration. Now in physics, there are many formulas that have force. Like work done is force times distance. Moment is force times perpendicular distance between the pivot and the line of action of force. Power is force times velocity also can. So there are two different types of forces generally. One is exerted force, one is net force. So you need to know whenever the formula has a force there, whether that force is exerted or net. It makes a difference. For acceleration, it is always net force. In fact, for most of the formulas that we have, is always exerted force, except for this. It's always net force. So what is the importance of net force? I'll give you an example. Now let's say you have a block of wood on the floor and you apply a force of 10 newtons. At the same time, there's a frictional force of 3 newtons. And let's say the mass here is 2 kg. So what is the acceleration? So remember, when you use F equals to ma, right? Now, whenever you find acceleration, you always need net force. Net force, acceleration, net force are always together. They're inseparable. In fact, there are only two quantities in physics which will always exist in the same direction, which is these two, net force and acceleration. Net force and acceleration must always exist in the same direction. You can never have them in you cannot have them in different directions. But you can have velocity and acceleration opposite directions. You can have displacement and acceleration different directions. Displacement, velocity different directions, but acceleration and net force always same direction. Do you understand that? Example, if an object is moving to the right, then the velocity is to the right. But if it is slowing down, then the acceleration is to the left. So it may be in opposite direction. But if your acceleration is to the left, then guaranteed your net force is to the left. It will never be in different directions. Do you understand? So that's the second one I'm telling you about. So anyway, so what is the force that we must use to calculate acceleration? Net force or exerted force? Net force, right now. So you should take 10 or 3 or 7? 7. So you must take 7 equals to 2a. So your a is 3.5. So that's what it means. You must always use net force to find acceleration. Never use exerted force. That means you must find out all the forces acting, then find the net force before you can find acceleration. Do you understand? Okay? Now, next one. If you say that F equals to ma is therefore second law, is also inaccurate. You cannot say F net equals to ma is the second law, because F equals to ma was only for constant mass. So we don't say it is second law, but we say it comes from second law. Because many people, when I ask them what is second law, F equals to ma, it's not. F equals to ma comes from second law, but it is not the full story of second law. Do you understand? Okay. Next one. From this equation, F equals to delta P over delta T, do you realize that I can bring the delta T over? So I will get change in momentum, delta P, equals to F times delta T, right? So it means that you can also find the change of momentum if you take F times delta T. But you can only use this formula straight away, provided your force is constant. If your force is constant, example, if I draw a F versus T graph, your force is constant, then you can use change of momentum is F times delta T. But if your force is not constant, example, let's say the force versus time was like this, you must find the area under the graph. That's what it means. Okay, now, to get the change in momentum. Understand? Also, from this equation, you can also get another thing. For example, let's say you have a graph of momentum versus time. So, straight line again, but not constant momentum. Because your F is equals to delta P over delta T, it means that the force is equal to the gradient of this graph. Do you understand? Delta P over delta T means this over this, which is the gradient. Understand? So these are all the relationships that you can obtain from Newton's second law. So summary, number 1 is a net force that causes acceleration. Number 2, the net force and acceleration must be same direction. Number 3, F net equals to ma is not the whole second law, it's only part of it. Number 4, if your graph of F versus T, the area represents the change of momentum. And number 5, if you have a graph of momentum versus time, the gradient represents force. Understand? So this is a summary of Newton's second law. Now you can also use Newton's second law to explain why you will feel heavier or lighter when you're in a lift. What do I mean? Now, if you are in a lift and then you're standing there, do you sometimes feel like you're heavier or lighter depending on how the lift moves? Example, if let's say you stand there, you press a higher floor, and then the lift starts to accelerate upwards. The moment it starts to move up, you feel heavier or lighter? Heavier. Correct or not? But just before the lift stops, right, you'll feel heavier or lighter? Lighter, so right now. That one's heavier, now it's lighter. Correct or not? So why? So this is called apparent weight, the weight that we feel. And the weight that we feel is because of this. Now, if I were to ask you, what are the forces acting on the passenger? Draw a free body diagram for the passenger. What are the forces acting? The weight and what? Normal reaction. So normal reaction force comes from Newton's third law, which talks about when you exert a force on the floor must exert back an equal force on you but upwards. You push down the floor, you push down on the floor will push up on you. That's called normal reaction force. So you have a normal reaction force, and it is this normal reaction force that we actually feel on our leg, correct? And which makes us feel like we're heavier or lighter. So now let's say it is accelerating upwards, because when you first press the higher floor, then it starts to accelerate up. So what are the forces acting? So you know your normal and weight. So which is bigger, your normal or your weight? You are accelerating upwards. Normal. So it'll be normal reaction minus your weight equals to MA, right? So your normal reaction will be your weight plus MA. That means the force exerted on your feet is not the weight that we have, but it's your weight in addition to MA. So we feel a larger force on our leg. That's why we feel heavier. Do you understand? That means you know what is the force that you're pushing down on the floor? You're pushing down with this as well. Because if the floor pushes you with this force, W plus MA, that means you are also pushing down on the floor with W plus MA. That means we are heavier. It's not our weight changing, our apparent weight, the weight that we feel is heavier. Now, just before you stop, what will happen is it will slow down. So if it slows down, we say the acceleration is downwards. Agree now? Okay? Now, if the acceleration is downwards, then which force is bigger? The weight or the normal? Weight or normal is bigger? Weight. So you take your weight minus the normal equals to MA. So the normal reaction force is your weight minus MA. That means the force that the floor is pushing up on your leg is the weight minus of the MA. That means smaller than your weight, right? Agree? So if the force that the floor is pushing up on you is smaller than the weight, that means the force that you're pushing down on the floor is also smaller than your weight. That means you feel lighter. Do you understand that? Okay? Now we can use this case for the other way. That means going down as well. So don't forget, if let's say the lift is moving downwards, and if the acceleration initially is downwards, because when you press the floor down, you start to accelerate downwards. When you accelerate down, that means the two forces acting on you, which is weight and normal, the weight will be bigger. So your weight minus normal will be equals to MA. So your normal equals your weight minus MA. So if the force exerted by the ground on your leg is less than your weight, so the force that you exert on the ground also less than your weight. So that means you'll feel lighter. But just before you stop, you will slow down, so your acceleration is upwards. So now normal minus weight equals to MA, because your normal is bigger than your weight. So your normal is weight plus MA, so you will feel the force that the floor exerts on you bigger than your weight. So the force that you exert on the floor also bigger than your weight. That means you feel heavier. Okay? Sometimes the question, instead of asking you for the normal reaction force or the apparent weight on the man, can talk about a mass suspended on a spring balance, and then they will ask you for the spring balance reading, which is actually the apparent weight. So instead of normal reaction force, what are the forces acting on the weight? So instead of normal reaction force, you just substitute with the tension. So the tension here will be the spring balance reading. Alright, so this will actually show you the apparent weight. So for example, let's say you have this lift here moving downwards and accelerating downwards with 5 meter per second squared. So which force is bigger, weight or tension? Since the acceleration is downwards, so weight will be bigger than tension. So then your equation will be weight minus tension equals to MA. So to calculate the tension, which is the apparent weight, we will bring the MA over, and then we will bring the tension over. So then your tension will be equals to weight minus MA, which means to say the apparent weight will be smaller. Example, let's say you have this mass of 1 kg, and the acceleration here is 5 meter per second squared. So we can substitute weight minus tension. So weight is 1 times 9.81 minus tension equals to 1 times 5. And then solving, you get tension is 4.81, which is actually less than the weight itself, which is 9.81.